Hello students, welcome back. Let us resume our discussion on linear mappings. First, let's have a review. In the previous lesson, in Module 7, we defined linear maps using these three conditions. 2.5 rather, because the third condition, as you can see, de-emphasized in gray, is not really important. Anyway, let's begin. A map L from one vector space V to another vector space W is called linear if it satisfies these three conditions. Number 1, it preserves the addition. Number 2, it preserves the scalar multiplication. And number 3, it preserves the zero vector. And the third condition here is unnecessary because you can always plug in C equals to 0 and deduce the third condition from the second condition. Or you can do what our textbook author did. You can deduce the third condition from the first condition. It's a little bit harder that way, but that was the choice our textbook author made. Not coincidentally, our textbook author is not considering the third condition as a part of the definition. He uses only these two. And that's fine with me. In any case, we have a well-defined concept of linear map, either using first two conditions or third condition, it doesn't really matter. We have well-defined concept. Now these three conditions can be reduced into a single condition like this. A map L from V to W is linear if and only if it preserves the linear combination. So if you want to shorten your proof, you can use this one so that you can prove all kind of things in a single step rather than three-step process. Okay, let's move on to the next topic. The matrix associated with a linear map. Let V and W be finite dimensional vector spaces. If they are infinite dimensional vector spaces, then it doesn't work. Finite dimensional vector spaces. V has to be n-dimensional with basis V1, V2, V3 all the way over to Vn, and W is m-dimensional with basis vectors W1, W2, W3, W4 all the way over to Wm. So n-dimensional and m-dimensional respectively. And finally, let L from V to W be a linear map. Then there's a unique matrix A, unique m by n matrix A, such that the map W equals to L of V corresponds to the matrix expression, the matrix multiplication Y equals to AX, where X and Y are column vectors, and those are coordinate vectors of V and W respectively. Now, the big thing, the key is, what is this matrix A? The proof of this theorem is long and complicated, but how to get the matrix expression A, that's important to everybody, even if you cannot reproduce the proof out of nowhere. And here's the scheme. All you have to do is to go back to the basis vectors, V1, V2, V3, V4, all the way up to Vn, and then find out the image vectors, L of V1, L of V2, L of V3, and so on, and then arrange those coordinates as columns, as a column, and then the second image vector as a column, and so on and so forth. The last image vector as a column. Then what do you get? You get an m by n matrix. There are n basis vectors, v1, v2, v3, all the way over to vn, and each corresponds to a column vector, so there are n columns. Are you with me here? First column, second column, third, fourth, fifth, sixth, nth column. So nth column here. And then W is m-dimensional, so the coordinate expressions of each vector in vector space W, including these L of V1, L of V2, L of Vn, all these, must have m numbers. So each column has m numbers, so there are m rows. So we have m by n matrix. Here's an example. a linear map from R2 to R3. So E1 is going to 1, 1, 2. E2 is going to negative 1, 3, 4. What's the matrix expression? There you go. A column and column, that's it. How about the next example? E1 is going to cosine of theta, comma sine of theta. E2 is going to negative sine of theta, comma cosine of theta. Again, the same deal. All we have to do is to get a column, and that's it. How about the next example? Well, we don't have f of E1 and f of E2 here. So we cannot get the matrix expression right away as we did kind of like this. We get first column, second column, and that was it. Instead, we have to use some algebraic process here because the theorem told us that the matrix expression exists. And how do you find out? Well, f of E1 is the first column, f of E2 is the second column. Why am I losing color here? Okay, that looks good. And then we can put everything into the matrix multiplication expression. A times x is equal to y, basically, yes. And then from there, you get two equations because this is two-dimensional column vector. Another matrix multiplication equals to y. So this is ax equals to y, basically. So what do we have? We have four equations and four unknowns. We can solve it using brute force method. And once you do it, we have this matrix expression. Okay, that was a quick review. Let me emphasize again, even if you forget the proof, everybody should know how to get the matrix expression. Go back to these basis vectors, v1, v2, v3, all the way over to vn, and then get image vectors. L of v1, L of v2, L of v3, all the way over to L of vn, and then arrange them as columns. All right. Now, we're pretty much done all the important topics, but we have a little bit of time left, so let's talk about composition. So, applying a linear map is equivalent to multiplying a matrix. So if I do it twice, then we have to multiply another matrix. That's basically it. Composition map, F first and then G. So multiplication by A first and then B, as you can see from here. Vectors of U is sent over to vectors of V, and vectors of V is sent over to vectors of W. So in particular, X is sent over to vectors on V, but it's done by the A times X by matrix multiplication. And then the second linear map multiplies B into this. So B times AX, that's what we have. But then again, if you use those associative property, then you can rewrite it as BA times X. And this matrix, BA, corresponds to the matrix this BA is a matrix expression of G composition of F. Now for inverse, it's exactly the same deal, except that in the end, we have to get original X back. So what kind of matrix B will give me identity? Well, that's A inverse, of course. So what's the conclusion? If the inverse map exists, then the matrix expression of the inverse map is A inverse, the inverse matrix. That's the conclusion here.